Hello everyone. Actually, I wasn't expecting that much of an audience. No pressure, okay. I'm gonna lie a lot. So sorry for that, because it's not going to be a presentation only about the animation, and also actually some of the techniques here will be applicable for Unreal Engine 5. So yeah, but still, we should be able to get used to lies, because game dev is smoke and mirrors, right? So let's start. Unreal Engine 4 and 5 is like one of the most robust and popular game engines in the world. And tons of AAA production, if not made on internal engines, quite often uses Epic's products. So along with Unity, Unreal Engine is the most, I think, important, free and worth using engine to make games in the world. And today I'll talk about small fraction of its functionalities in the area of management, calculation, rendering, and animating many repeatable objects on the screen, because my passion is squeezing out the most of the engine's possibilities in large-scale solutions. So let's go with that. So here's a plan of my lecture. After introduction, I'll tell you about basic assumptions to explain why we're pursuing specific route with our implementation. Then I'll talk just a little bit about engine characteristics and terminology. I'll tell you about significance manager, which is the basis of everything else you'll be hearing here. AI and navigation, animation, renderings. There will be a small summary, and then time for questions and answers. So let's begin. You probably don't know me, maybe, hopefully. So hello, my name is Grzegorz Wątroba. I'm a programmer for around 12 years now. I did a bunch of projects for different platforms using multiple engines and languages. Here's a list of companies I was cooperating with through that time. And that's about my introduction. So because we don't have much time here, and there's a lot to talk about. So let's explore our basic assumptions and motivations for this lecture. So our goals are, we are making RPG in a big city, and we have on a level around 1,000 units, and up to 200 may be at the same time on the screen. They are fully animated. They have individual schedules and properties, and they use modular submeshes, which are partially procedurally generated. So there would be a problem if we use animation sharing. So we're not going to pursue that. And every unit has its own schedule. Each unit can move around entire level, react to player, and interact with him. And of course, as we try to reach industry standards, we want to have 60 FPS both on Full HD and 4K resolutions. So yeah, so all in all, we want to have everything nice and dandy, right? Also, solutions applied here and described might not be universal for every type of project, but as you can see, we want to reduce cost of everything and still have it look quite good, hopefully. So remember during your own game development what kind of game you are making, to know where to cut out all your redundancies in engine's functionality. All presented solutions here are implemented, tested, and verified in our current project, Project Vitriol. I want to emphasize that those solutions described here are not only my private ideas and implementations. To achieve those results, many former and current programmers from Fool's Theory were putting their hearts and souls into the project. And for that, I'd like to thank them because of their effort, advice, and building foundations from which I could push things further. So thank you guys, because I think there are a few of them here. So thanks. Okay, let's describe some of the engine mechanics to be more aware of challenges and definitions that we will face during this presentation. So engine is written in C++ and has open accessible structure and code, of course. It's very modular, allows to turn on and off many partial functionalities on demand. It's object-oriented and relies on actor-component relation, where every actor and component has its own update phase. Everything is mostly built like according to our human intuition. So we have some character and it has certain properties, and those properties are like joined to it, and then to access it you have to sometimes go over the memory too much, in my opinion. So we have to fix that. We can control each element of the object separately, you know, the state management, update mechanics. We can even turn off the garbage collection if we have courage. But remember, with great power comes great responsibility. These those are the basic elements of actor's lifetime, but number of methods that are used to process is much greater, and each of them comes with some overhead cost. So we don't want that, or we have to reduce it to the maximum. To avoid this overhead, we can do certain things. Either turn the ticking completely, turn on and off specific elements, or change update interval, which is very convenient, and we will be using that a lot. While looking for optimization solutions to process repeatable instructions in a big scale, I explored 3 areas: multi-threading, data-oriented computing, and heterogeneous calculations. So multi-threaded process is possible in Unreal in many forms. Parallel for, async task, or runnable structure are like the basic ones. Each technique is useful in different ways, in different situations. So the parallel for is like the simplest one, allows to do multi-threaded processing within array. It's worth using it for like the large set of data, or if task per array element is heavy. Remember to never modify size of the array, but you probably already know that during for instructions you shouldn't do that as well. But if you have to modify the element of the array which could be read somewhere else, you have to create a critical section with mutex. Async task is more like fire and forget multi-threaded solution. We do not necessarily control entire process, but we can delegate feedback to main thread at the end. Runnable, of course, is the most complex solution to control entire process. And why even bother? So many tasks in game, when properly set up, can be done on separate threads, and then we can just make it a few times faster. For example, pathfinding. And remember, do not meddle carelessly with memory on threads different than main or game thread. Data-oriented programming is like the form of optimization on large dataset. If we can pack the data in memory next to each other, then we're using CPU cache and prefetching. That can use, and then through that we can use vectorization. So meaning the SIMD operations, single instruction, multiple data. That way, for example, instead of multiplying within one processor cycle, instead of making like one division or multiplication, we can pack a few set of data at the same time and then do it directly within one calculation cycle, and that makes it like 4, for example, times faster, like straight up. And Unity uses for it burst compilator, and Unreal uses ISPC, so Intel SPMD program compiler. This is like the already in Unreal Engine 4.27 for sure. I don't know from which specific version ISPC is already like inherent for the entire engine. Still, in 4.27 you can utilize ISPC without problems. You can just find examples of using this technology within the engine, so you can copy from that and try on your own. Then, aside from this kind of vectorization, you can also try to use entity component system, which is architectural design pattern where we can organize data differently, granularize it so the component is a single property, and entity is like database entry. So to speak, that filters out the set of components needed to calculate specific functionality requested by system. So one of the biggest profits here is potential to use SIMD and reduces tick count, because instead of doing, for example, 1,000 updates, we can do one update for 1,000 units. So it's like reversing certain psychology for calculations. And Unreal Engine 4 uses it to some extent, for example, for sequencers and animation, which we will address later. And fifth iteration of the engine, in addition, uses it, for example, in AI logic through mass AI system. Currently, we can also use ready solutions like Flex, or customize our own functionalities, which we are attempting here. So let's go to the heterogeneous calculations, where we use two different types of compute units. In our cases, logically, is CPU and GPU. GPU can be utilized in at least two ways. So first are compute shaders, which use very specific instructions separated from standard rendering pipeline to provide calculations, and they work best on array because, you know, doing, for example, texture modification is just an array of colors. So the same way we can do for calculating like anything else. And second are specific compute units present on, for example, NVIDIA cards called CUDA cores or AMD cards called compute units. And each GPU manufacturer, even though has its own specific technology, OpenCL can use both of them. So that's why we prefer using OpenCL, and we are meddling specifically with this. Using those two solutions can be tricky, but when properly adapted, it can be really beneficial. So if you have time, if your boss will accept, for example, a few days of experimentation in the project, try to use that if you have some en masse solutions. And also, both technologies for Unreal have quite convenient plugins, so it's worth the shot. Since we got to know the basics, let's focus on a bit on measuring techniques, because without them it's hard to verify whether a given solution is worth doing, right? So common way that gaming people measure performance is with frame rate or frames per second. And this actually can be quite deceptive, because if you have, for example, 900 FPS, this translates to 1.11 milliseconds of frame time, right? And if you have 450 FPS, so half of that, it's 2.22. So this is quite weird, because if we have 60 FPS, we have 16.66 milliseconds, and if we have 56.25 FPS, we have 17.77 milliseconds, so the difference is quite the same. So here and here we have 1 millisecond point 11, and still the difference in FPS isn't that dramatic. So this is why we should actually measure things in frame time, unless we are going out the frame budget. So remember to focus on the frame time to measure how fast your game is running, and stay within the frame budget you wanted. So if you assume that you have 60 FPS on Full HD and 30 FPS on 4K, hold to it, but measure things and measure the performance gains in frame time. And to properly measure performance, we use 3 basic tools. So standard Unreal Profiler, which produces stat files through Profiler. In Unreal frontend, we can see the cost of instruction execution, and we need just 2 simple commands. So start file, stop file, and we have this nice statistics file, which we can analyze further. Next thing is Unreal Insights, a much more advanced tool in my opinion, which allows us to connect the editor to connect to editor or build game and measure time cost ad hoc. We can measure loading times and GPU instructions. So this works both for editor and cooked versions. So we just need to specify a simple parameter. You can see that on the screen, and we can through that extract the performance data. Last but not least, RenderDoc. This is like my favorite external tool, but you can use anything else. Still, it's worth to use Profiler, mostly focused on GPU. A tool that can do a snapshot and analyze data stream and measure instruction cost. Also, we can do it in editor and cooked version. So we can go to the point where we can measure cost of viewing simple mesh, for example. So it's also worth analyzing and playing with. Measurements without testing platforms wouldn't make sense, right? So currently, while I was working at home, I had 3 different tiers of equipment. From 5-year-old mid-type crappy grid to modern upper mid-level configuration of sorts. Also, we will test performance on 1 unit, 50 units, and 200 units on the screen. Times will be given in milliseconds and compared between unoptimized and optimized versions. Results can be sometimes fuzzy, and as you can see, we don't have exact same types of CPU and GPU to compare between tiers. So it's not like lab quality of testing grounds, to be honest. That's why I was talking about those lies in the beginning. Further down the road, we are working on automated testing machine, which will provide better results and more accurate things to compare. Still, it is noticeable that certain solutions work even at unfinished stage while being quite cost effective. It is important to remember to isolate to maximum extent functionality you're testing. So if you're testing some CPU-bound solution, try to not render anything, or at least turn off to the max number of graphical effects. Limit also those unnecessary fuzz arounds from other instructions, because when you have this some functionality isolated, then you can measure it better. So there's that. So after theoretical introduction, gladly we're over about that, it's time to go to the main course. So first, the foundation of many optimization techniques in our project, Significance Manager. Actually, because I was actually asking developers from other companies, this is not like custom thing, it's engine, Unreal Engine's Epic solution. So this allows to register and calculate how important the object is within the current point of view. The less significance, the less resources we can use for processing. So it's crucial to write proper function to describe importance of an object. Position from the player is not enough. Aside from distance, it is advised to utilize the camera frustum or sight range or something strictly connected with visibility, since we see objects in FPP games completely different in comparison to isometric games. System is very light, quick to access, and gives great foundation to optimize objects. Yeah, Yeah. So to configure significance manager, you have to turn on the plugin and create on game viewport client, since it will make the whole object to view relation easier to implement. So the core of it is to feed SM with data which will help us calculate this significance. So this is like everything you need at this point to make like the most simplistic assumption. So it's not that much. Next, object which we want to react to and calculate significance change, it has to be registered. So in begin play of an actor, preferably, but you can do it in different places, but this is like advised by Epic. You have to set up two functions, calculate significance and post significance. Calculate significance takes data from viewport client and compares it with current object state. Then we calculate this significance coefficient that will describe in which bucket we place object in. We use three. Like I showed it in the previous screen, high significance, mid, and low. So low is like we basically don't need it, but we have to handle it somehow. Post significance method allows to react to calculated coefficient and modify certain things on this object. So turn something on and off, raise or lower TIG interval, and so on. We utilize that technique in many different game elements, so from animation and logic to the priority of initialization actually, because we spawn certain units within the runtime, and based on the significance we can prioritize which characters we want to show at the start, and then asynchronously spread out the rest of the frame time to spawn other elements. So now AI and navigation. So pathfinding is one of the more costly problems in games, especially when we have lots of units and complex terrain architecture. And I'll try to describe now the solutions we use, tests or plan to implement, because we're not done here. Still, yeah. Behavior tree system is the functionality that Epic provides. Is very versatile and nice to work with, but actually we completely don't need it. What we need is just instructions, go from point A to point B and run animations, and that's it. That's why we created our own system which manages movement calls and runs animations. Joining it all together with subsystemic AI manager, I mean AI manager is a subsystem, world subsystem. We have full control over the process. Thus we do not need that comfy, nice graph-based system. We just let our designers set up action points on map in this unified system, and proper organization reduces tick usage, regulates those points based on significance, and gives an opening for multi-threading because the data regarding it is packed nicely next to each other. Regarding the navigation, we also have custom solution that splits terrain into simplified grid, which gives us opening for simplified pathfinding. Also, we have it arrayed, so we can do it with different techniques. And we try to play around it when you have time. We don't have much time, still we try. First and simplest solution, of course, is limitation of AP update within chosen ranges. Most of the time we use 3 ranges, as I said before, and update it within given time interval respectively. And APs of higher significance are updated every frame because they regulate how units move around. Then mid-range APs are updated every quarter of a second, and least important every second. Then that's why we are actually quite cost effective, because units still move around the entire city, but we don't see that units actually leapfrog every second, and we don't have to calculate all of this mess every frame. So, pathfinding optimization. For pathfinding, we use A-star algorithm, currently single-threaded, but we play around. And since we need to be time effective here and don't have a lot of time for do fun stuff, because we have other fun stuff to do, we went for cheapest optimization, so rewriting core of A-star pathfinding to be multi-threaded. Even though it's not final implementation, results are quite promising. Still, we are planning, since we have grid, we want to do it on GPU. So let's see basic single-threaded measurements, and those gains are a result of using custom solution, cutting out the call overhead only. So it's not much, but it's still not bad either. As you can see, in larger scale, we have like 10% of frame time gain. And when we do multi-threaded solution, then we can reach out to 66% of gain. Still, this scaling isn't quite right, I know, but probably we have some problems that we are missing here. Still, as you can see, in the cheapest attempt to optimize stuff, we already have quite nice results. Also, as you can see, for a single unit, there is not even quite chance to have any gain, because the cost of setting up the threads is affecting the 1 unit calculation, but it's not scaling that much if you scale up the number of units. So it is becoming less significant as the number of units rise up. The main thing, and the thing that's actually adaptable not only for programmers. So why do I want to focus on this that much? Is because our units, our NPCs, do not have much of AI demand, because, like I said, run around the city and play animations. But like I said, play animations. We have complex stack of animations to play around, because we want to present the time schedule. We relate those actions of NPCs according to time of day, the type of weather, and so on and so on. So we have we are quite demanding here, and we want to squeeze it out to the max. So animation blueprint is a specific asset type which we can operate comfortably with animation states, blend sequences, and animontages. It allows to blend unit states fluently and join different kind of animation techniques. In our project, almost all our units use one common anim blueprint, which makes it easier for us to explore data-driven areas and multi-threading. Bear in mind that AnimBP is not suited for calculations, and this is like the common mistake that people squeeze therein. For example, adding some stuff, comparing some stuff. Do not do that. If we can, entire computation should be present in anim instance, which is the native parent of anim blueprint, and anim blueprint should only react to data. If we do this properly, AnimBP will automatically use a thing called fast path, which optimizes access to animation data. As you can see on the screen, this warning on the lowest image shows that even making a comparison to 0 value already raises a warning. I will tell you later how to turn this on to see where you have those AnimBP inefficiencies. The best way is to either use unit blueprint to calculate stuff and then let AnimBP to access those data and only react to it. Even better if you write everything in native code and just show the values to AnimBP wherever it's possible, but do not calculate there anything. In project settings, we need to set optimize anim blueprint member variable access and allow multi-threaded animation update. It's crucial to also check use multi-threaded animation update and warn about blueprint usage, which will allow us to do multi-threaded animations and will warn us wherever we are doing something inefficient. So this is like free to do and actually really worth it doing. Here you can see how the setup of it looks in game mode in native code. While utilizing settings for designers, they could tune up system parameters without programmers' help. And this is also to set up significance settings, which will be useful in a minute. Also, as you can see, it's just a few lines of code. Actually, you can copy it. I forgot about one thing. You don't have to make any notes because I will let you download those slides in PDF format. You will see QR code in the end and link to download it. So you can just sit back and enjoy. So anim instance and anim instance proxy. How those structures work and how they relate in unit BP, this diagram should explain it a bit. So as you can see, unit BP is like the main unit's logic. Then it uses anim blueprint to operate on the animation. And anim BP inherits from anim instance. And within it, there's anim instance proxy. And why do we need that? It's a structure which holds data and parameters for animations, which are prepared before animation frame and then read in non-blocking way in multi-threaded processing phase. You should pack there as much parameters as you can, because through that you can actually delegate all animations in your game to multi-threaded phase, which makes it really, really cheap. After that, we have synchronization fence, of course, and post-update instructions. Everything is really easy to use. There's just, again, a few lines of code and should be quite clear. Ask your local programmer. Yeah. So through FastPath, also, we can access data very quickly in a thread safe matter, because if you properly set it up, you can do like registry binding from proxy directly to React in Anim Blueprint, which also makes it all faster. So it's really advisable to do that. Next really nifty thing is budgeted skeletal mesh. So budgeted skeletal mesh is automatically connecting to significance manager and based on previously established rules, reduces time frame used for animations to save the calculation overhead. What is interesting, this system automatically distributes animation precision, which makes it much easier to test optimization. We can just set up that we want cost of entire animation processing to 2 milliseconds, and that's it. And the system will automatically change the precision of the animation, which is really, really nifty. And then update rate optimization. So this helps to improve the priority of update calls for given animation and prevents animes from ticking too often. So if you'll do all this magic and still not experiencing much gain from the entire processing, go to method needs immediate update. If this horribly looking method returns true, that means you messed something up and you have to check what and fix it. If it will return false, then you have fully multi-threaded animation processing, which you really want. Yeah. So let's see our measurements. Again, we see that for a single unit there's no gain at all normally because the setup of it costs a bit. But when you go further with numbers, you see that there's a quite nice gain. Also, you can see a strange thing in the last column. Like I said, we've set up the cost of the animation to 2 milliseconds, and that's it. The only thing that changes regarding the hardware is how nice the animation looks. Still, there are some inherent techniques that makes it still not looking horribly, so your eyes won't bleed. Since we have not much of a time, I think I'll handle it. Rendering. I wasn't focusing much on it because the animation was like the core of this presentation. Still, in rendering area, we can also have a bit of gain. Of course, this is like the basic stuff, so you have to use LODs. If you are using Unreal Engine 5, this is like not needed. This is not needed for static meshes, still applicable for skeletal meshes, but I think that Epic won't rest until they will apply Nanite to skeletal meshes, and hopefully they will achieve that because it would be awesome. Still, you can generate LODs directly now in the engine. You don't have to use any entire external software. Also, remember to use culling and simplify colliders. You can use this nice one flag that can be set up on the mesh, which has this very romantic name, B component use fixed scale bounds, which makes it much easier to calculate culling, because we have those two types, basic types of culling. One is frustum culling, so if something is out of the camera, then it won't be rendered, so we have benefit from that, and also occlusion culling, so if one object obfuscate another completely, then it also won't be rendered, and this is like the default setting in Unreal Engine. So yeah, but still, if you set this nice nifty flag, then it will make it a bit lighter. Also, FSR and DLSS. Both AMD and NVIDIA provide for Unreal very convenient plugins. This is actually regarding the first iteration. Now we have FSR 2.0, DLSS 2.0, which is even better. But still, I'm just waiting for plugins because I'm lazy. I'm not lazy. I'm just don't have time to meddle it completely from the scratch. But still. AMD will provide plugin probably soon for Unreal Engine 4 and 5, so I'm just waiting for that because those solutions actually can be implemented within half an hour, so it's like free performance if set up correctly. In our case, through that we have this perspective to have 60 FPS both on full HD and 4K resolutions, and overhead of the calculation is not lowered that much, but cost of rendering really makes the difference here. So without any quality loss or not so visible quality loss, we can achieve even 30 gain of performance. Actually, we had one problem because we are using AMD's FSR. If we have character which has beard and it's sparse, then we can notice that there are some fuzziness there and doesn't look that well, but there are certain parameters that can handle it to make it look better. And again, let's measure it. So the results are also affected by different effects we use in games, so it's worth to turn all effects off for the sake of measurements. And also the results may differ in scene-to-scene basis, because it's not like the FSR 2.0 is complete reconstruction of the the image, and FSR 1 is like upscaling technique mostly. So this depends on the things that you're rendering at the given time, and this is just average of certain measurements. And on the left side we have no culling technique, no upscaling, no LODs, and on the right we turn that all on, and we have around 30% of gain. Also, this can be made better, and probably if we move to Unreal Engine 5 and use FSR 2.0, we will notice even better results. So, let's summarize it. Techniques presented here may not be in entirety applicable in your games, but some of the solutions might be universal and some in proper context after appropriate adaptation. Remember to adapt to your genre, experiment and measure performance to verify your theories. And you can see here how the weight of specific processes look like in currently most optimistic scenario. Still, it needs work, I know, since not every part of it seems right and to my personal liking. Still, this is not as much work as you could think, and as you saw in numbers, there's quite significant gain. Sadly, since we are not announced yet fully, I couldn't show you any screens and any recordings of these techniques. Still, please follow our page, our social media, and my social media. I'll probably show them around when we can. So, of course, we are hiring, and you can download the slides by scanning QR code on the left and look for opportunities when scanning the QR on the right. You can always contact me in person. I'll be around, so yeah. And here you have links. I mean, links for all the sources I use for presentation. All of the information will be on the slides, so thank you for your attention. And you can always find me on social media or reach out to me in person if you have any doubts or remarks. Probably you will. And yeah, so you can scan it, and now we have time for questions and answers, but please allow me just to take a sip of water.
Thank you, Grzegorz, for your presentation. And if you have any questions, you can please stand up and come here on the stage that everyone can hear you.
Hi. If I understood correctly, you are using both compute shaders in some, I don't know, GLSL, HLSL, and also OpenCL, yeah, to do computation, or no?
Not at the same time.
Okay.
Currently, we are just using multi-threading and planning to use either compute shaders or OpenCL.
Yeah, because my question was, why not to stick there just to compute shaders, yeah, not to mix both, yeah? Because then you have to use some interoperability between both.
Exactly. So
yeah,
we will use one or the other.
Ah, okay, okay.
Yeah.
And if I can, second question, because you said that, and of course it is, this overhead to create threads, yeah, is quite huge. And these threads are created every frame? Is it possible to create them? Okay, I know that it's possible somehow
Yeah.
to create threads at the beginning and then skip with these threads.
Yes, and this is like our basic mistake. We are not doing it every frame, but still we are trying to utilize subsystem to manage the threads and just hop in with the data we have this synchronization cycles, and threads are run once and then fed with data every now and then, but still we are trying to make it less fenced to make it more fluent, because those problems with scaling are probably the result of not doing it efficient enough. Yeah, so yeah, we have this field of improvement there.